In the last video, we defined an equivalence relation on a set and we saw some examples. Let us next see this example. It's a very important one. You won't really realize its importance right now itself, but later on if you go to study higher mathematics, there you will see why it is important. But anyway, let's see the relation first. The set on which this is a relation is the set of integers. And the relation we are calling it R1. In the book it's given as R, but there is a similar relation, another one. So I have decided to call it R1. What is R1? It relates to integers A and B if 2 divides their difference. Okay, it may look like a very arbitrary thing to define a relation like this, but apparently this is an equivalence relation. Let's see why. Let me just show you the main steps without writing sentences because they are already available in the book. What are the 3 things we need to show? We need to show that the relation is reflexive, symmetric, and transitive. What is reflexivity? Reflexivity tells us that this should be true for all integers A. Is it true? Let's see. Since 2 divides 0 and 0 is A minus A, for any integer A minus A is equal to 0 and obviously 2 divides. Oh, I forgot to tell you. I cannot use this note. See, this is the problem. I cannot use that notation. I have to write since 2 divides A minus B. Let me keep this, okay? Let me write from here. Since 2 divides A minus A, okay, for every A in Z, so this belongs to R1 for every such A, and that is why R1 is reflexive. What about symmetry? Symmetry means you choose an ordered pair in R1. You then have to prove that B comma A also belongs to R1. Now what does this mean? It means that 2 divides A minus B. Will 2 then divide B minus A also? Yes. For example, if you have 12 here, 12 is divisible by 2. Minus 12 is also divisible by 2 because minus 12 is just minus 1 times 12. Then 2 also divides B minus A. So this also belongs to R1. That means our relation is symmetric as well. And that leaves us with transitivity. For transitivity, we take this. This means that 2 divides both A minus B and B minus C. Actually, there is another way of expressing this sentence, or in fact the definition of the relation itself. 2 divides a minus b. Instead of saying it like that, you can also say that a minus b is an even integer. So now we have 2 even integers, a minus b and b minus c. So their sum will also be an even integer. Plus b minus c, which however is a minus c. Thus, this belongs to R1. So R1 is also transitive. And so being having these 3 properties, R1 becomes an equivalence relation. Alright. Now let us consider 2 special sets. One of them is E, the set of all even integers, and the other one is O, the set of all odd integers. Excuse me. Why are we suddenly bringing these sets here in this discussion? What do they have to do with this relation? Well, we are going to make 3 observations about these sets and how they are related to this relation. The first observation is this: any 2 elements of E are related. Any 2 even integers are related to each other by our relation. For example, if you take 12 and 24, then their difference, 12 minus 24 is minus 12, that is divisible by 2. So 12 is related to 24. Like that, any 2 even integers are related because the difference of any 2 even integers is again even. It's a simple fact. Also, any 2 elements of O are related as well. Just like the difference of 2 even integers is even, the difference of 2 odd integers is also even. For example, 3 and 5 are odd and their difference is minus 2. Minus 2 is divisible by 2. So 3 is related to 5, which you can express by writing this. Any 2 odd integers you take, they will be related to each other. So the set E seems to have gathered some integers such that they are related to one another. Any 2 of them are related. The same property is shared by the set of odd integers. However, no even integer is related to any odd integer. No element of E is related to any element of O and vice versa. That is, no element of O also is related to any element of E. It is like 2 groups of people, okay, who have formed very close bonds among themselves. In one group, that group is called E, everyone is everyone's friend. In the other group also, everyone is everyone's friend, but no person from group E is a friend of anyone from group O. They are in fact enemies. Okay, in that sense you can think of these sets. And there is one more thing to note about these two sets. It is that two things actually, they are disjoint. There is no integer which is even as well as odd, and their union is the entire set of integers. In other words, every integer is either even or odd. Okay, but so what? What is so special about these sets and they are linked to that relation? Let's see another relation on the set of integers which is similar, but this time we are not going to divide by 2 but instead by 3. Consider the relation R2 3 divides A minus B. Okay, in an exactly similar manner, you can also prove that this R2 is an equivalence relation. In fact, I want you to do that. Okay, you go through the details of how we showed that R1 is an equivalence relation and repeat those same things. Repeat means not exactly, of course. Adapt that proof for this R2. Okay, so you do that. So we simply assume that R2 is an equivalence relation on the set of integers. Now, just like these two sets of even and odd integers, this relation also has such sets. Let's see. In this case, we will get 3 sets. We seem to be getting as many sets equal to that number. In case of this relation, let us consider these 3 sets. Let A1 be the set of all integers of the form 3n, where n itself is an integer. So that means A1 is the set of those integers that are divisible by 3. A2 has integers which look like this. These are not integers divisible by 3, but each one of them leaves remainder 1 when divided by 3. Okay, so these are that type of integers. And finally, A3 consists of those integers which leave the remainder 2 when divided by 3. These sets also have those properties. The first is that any two elements of AI are related by this relation R2. In fact, let me just write by R2. 2. Where you can of course understand what I is. I can be 1 or 2 or 3. Okay, so that means we are saying something simultaneously about all the AIs. Number 2, no element of AI is related to any element of Aj if I is not equal to j. We did not write vice versa because in this case that's not necessary. The statement in general for I and j already includes that. And number 3, any two such sets are disjoint and their union is the set of integers. Well, is it really true? Are these things really true? Let's see. We said that any two elements of say A1 are related. You take any two elements there, 3n1 and 3n2, where n1 and n2 are integers, positive, negative, anything, 0 even. You take their difference. Is this number divisible by 3? Yes, because it is 3 times another integer. Is it also the case? So that means these two integers are related by R2. Is it also the case with the elements of A2? Let us take two elements of A2 and see their difference. You will see that the difference is again a multiple of 3. So yes, they are also related. Any two elements of A2 are related. What about A3? If you change this is how any two elements of A3 will look, and you get that same thing. So yes, the first statement is true. Why is the second statement true? No element of AI is related to any element of Aj. Is any 3n related to any 3n plus 1? No. Why? Well, let's see their difference. Let me write say 3n1 is any element of A1 and any element of A2 is 3n2 plus 1. This is of the form minus n2 minus 1. If I claim that this entire number is divisible by 3, then already 3 divides this part, so 3 would then have to divide minus 1 as well, which is not true. From properties of divisibility, 3 would then have to divide minus 1, which is not true. And that is why this is not divisible by 3. So 3n1 is not related to 3n2 plus 1. In a similar manner, if you take the difference of any number of this type and any number of that type, that difference also is not divisible by 3. So no element of A2 is related to any element of A3. And by a similar argument, no element of A3 is related to any element of A1. The third observation, of course, is very clear. These sets are mutually disjoint and their union is O. How is this true? Well, this is true because you already know it from your elementary school arithmetic. When you divide any integer by 3, what are the remainders that you get? What are the possible remainders? 0, 1 and 2. Accordingly, that integer will look either like this or this or this. This means that any integer will either be in set A1 or A2 or A3. That is why the union is equal to Z. But what's going on with these sets? And how are these sets arising with these equivalence relations? Let us see this a little more closely. So far we have seen two equivalence relations today, and some sets which are somewhat mysterious, which are appearing with them. Let us consider this general situation. Let A be a set and R be an equivalence relation on A. Okay, fine, it's a simple matter. There is a set and there is an equivalence relation. Let X be any element of A. We are now going to define something new. The equivalence class containing X is denoted by this notation, and what is it? And is defined as this. It is the set of those elements y in A such that x comma y belongs to R. In other words, the equivalence class of X is the set of those elements of the set A which are related to X. So if we think of the relationship as a kind of friendship, then the equivalence class of X is the set of all friends of X. You can notice something immediately about this set. The first thing is that it is a subset of A. It is not, see, we are no longer talking about ordered pairs. Yes, you do see an ordered pair here, but the elements of this set are ordinary elements of A, the friends of X. The second thing, because our relation is reflexive, so for any X in A, X is related to X, and that is why X itself belongs to the equivalence class of X. So any element of A you choose and look at its equivalence class, there will be at least one element which is X itself. So maybe there is someone alone, but at least that person is his or her own friend. Okay, we are assuming that that's always the case in this analogy of relationship with friendship. Okay, so that is one thing you get to see about these equivalence classes. There are some other properties also that the equivalence classes for any equivalence relation have, and those properties are those properties that we saw just now. So the sets that we saw for the two relations R1 and R2 on Z are actually the equivalence classes. The set E, I am talking about the relation R1, is in fact the equivalence class of the integer 0, and the set O is the equivalence class of the integer 1. It turns out that these two are the only equivalence classes. No other equivalence classes exist in this case. So this is for the relation R1. For the relation R2, the set A1 is the equivalence class of 0 containing 0. The set A2 is the class containing 1, and the set A3 is the class containing 2. In this case, these are the only three distinct equivalence classes. Well, you may question, what if I take another integer, say besides 0 and 1 for the relation R1? Let me say take 3 and consider the equivalence class of 3. Is it not different from 0 and 1? Actually, it's not different. Let's see how. So, what are the elements of 3 in this equivalence class? These are the elements y in Z such that 3, y belong to R1. And what is that? Well, 3 is related to y. We already noted something about the relation R1. Two even integers are related to each other, two odd integers are related to each other, and no even integer is related to any odd integer, and nor is any odd integer related to any even integer by this relation R1. So from those properties, what can you say about this set? Shall we have any even integer y here? No, not possible, because then y would be related to 3. But that goes against what we said about the set E, the relation R1. So no odd integer belongs to this set. What about, no even integer belongs to this set. What about the odd integers? You take any odd integer and take its difference with 3. That difference is even. That means it's divisible by 2. So that odd integer will be related to 3. So every odd integer belongs to this set, and no even integer belongs to this set. What does that mean? Because we have only even and odd integers, this is precisely the set of odd integers. And that already is 1. So you don't get anything new, you are actually getting this equivalence class. So you can already guess what's going to happen if in place of 3 you take another odd integer, say 5 or even say 1001. You are actually going to get just this set, nothing else. Similarly, if you take an even integer, you will get its equivalence class equal to E. And in a similar manner, you can show that these are the only 3 equivalence classes for the relation R2. Okay. These things, I think, in fact, are explored in more detail and in a more general manner in one of the exercises. So the authors have decided to not really pursue this anymore now itself. Okay, so the example stops here. There is one more example with which this section itself ends. In that example, you have a set. Let me straight away write the set. 1, 2, 3, 4, 5, 6, 7. And there is a relation on A. the relation is this. A and B are related if either A and B are both even or both odd. Do you see that this R is actually nothing but this R1? The only difference is that R1 is defined on the entire set of integers, R is defined only on this. Why? Because we ultimately came to know that R1 relates to even integers and to odd integers, but does not relate any even integer to any odd integer. That is precisely what R also does. And what will be the equivalence classes here? So just like this one, here also there will be two equivalence classes. One of them is the set of all odd integers in this set, which are 1, 3, 5, 7. And the other equivalence class consists of the even integers 2, 4 and 6. You can see that in this case also those properties are true. Any two elements from this set are related. In fact, by definition, any two elements of this set are also related. No element of this set is related to any element of this set, and these two sets are disjoint, there is no common element, and their union is A. Okay. We will have more to say about these properties of equivalence classes later on. So this is where the section ends, and after that we will solve exercises. But anyway, that's just it for tonight in this video, and tomorrow I think it's commutative algebra, but I don't know, I keep forgetting things. Okay, so we will see what it is tomorrow. So see you tomorrow. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.